Hi guys, today we will find the electric dipole field and show it's only an approximation of the scalar potential. So let's begin. The scalar potential in the discrete form is only a summation of all the charges over the distance. Okay, I will define a function f of r minus r tag equals to 1 over the distance. We can say it's merely this part from the scalar potential. By Taylor expansion over the r tag, we get f of r minus r tag dot the gradient of f r plus the second order. This one, the first order of approximation, and this one, the zero order approximation. I'll just write it like that. Okay, now I will solve a little bit mathematics here. The gradient of this function is equal to the gradient of 1 over r. Because this function depends only on r, the gradient is only the derivative by r. For 1, I will just write r here, and don't forget the unit vector. And this equals to minus r divided by r cubed, r squared. And we can write it as minus r vector divided by r cubed, because we know that the unit vector is actually the vector divided by its magnitude. Okay, and the first function, it's only 1 over the magnitude of r vector, it's 1 over r. Okay, if we just back to here and substitute it on the potential, we get that the potential is the summation in all the charges over r plus the summation in all the charges dot r tag over r cubed. Okay, here we get that the summation over all the charges is actually the total charge over r. And this is merely the Coulomb potential plus another q I, I'll just write it like that, dot r divided by r cubed. Okay, I will define here this vector equals to summation of qi r tag, that's it. And this is the dipole momentum. This vector actually is the dipole momentum. We just define it as the summation over all the charges multiplied by the distance of every charge. Okay, I will write here the phi, it's equal to the total charge divided by r plus the dipole momentum dot r over r cubed. Okay. We will need this result. Okay, this one, as I said before, it's the column potential, and this one is the dipole potential. And once we get the dipole potential, it's so easy to find the electric field, because the electric field is equal to minus gradient the potential. And if we want to find the electric field of the dipole potential, we just can write just something like that. And another time we just calculate it. The gradient of the dipole momentum dot r divided by r cubed equals to, it's just like a derivative, so we can derive this and then derive this, just like the derivation of the first term dot the second term plus the first term dot the derivative of the second term. And it's actually equal to the derivative here, it's by r, not by r tax, so it's just like the moment dipole, it's just like a constant and this derivative, so we can just write it as p over r cubed plus p dot r dot this derivative, it's only just minus 3 dot 1 over r4. Okay, it's just only a simple mathematics here, and we get r in 4, and here we get r p minus 3, and here we get, oh, I just here forgot to write our unit vector from the gradient, and here we get 3 multiplied by the r unit vector multiplied by p dot r. Okay, as I said before, the unit vector is actually equal to the vector divided by its magnitude, and we can write it here as r p minus 3 r vector over r p dot r over r in 4, and it's equal to r in 5 p dot r squared minus 3r dot r dot p. And don't forget the minus here. So we get that the electric field of the dipole equals to 3 r dot p minus p dot r squared over Rn5. This is the electric field of the dipole, and this is the potential of the dipole. If you have any question about the calculations, so please leave a comment, and I hope you enjoy it. Thank you for watching. Don't forget to like and share and subscribe. Thank you so much. Have a good time.